Okay, for those that are watching the recording, you didn't miss much. This is the first slide. Okay, so how to find singular values. You diagonalize A transpose A, or you can diagonalize A transpose. They'll give you the same singular values, and the eigenvectors will be singular, what are called singular eigenvectors or singular vectors. So the eigenvalues of either, I'll say A transpose A, are square roots of, or squares of singular values. I'll say. And the eigenvectors are will be the columns of either U or V. So these are called singular vectors. And if you do it for U, A transpose, this will be the columns of U. I guess you have to appropriately normalize these. So it should be normalized. So because you want U and V to be orthogonal, so you want these to be unit length. Okay, so why don't we look at A transpose A? Let's multiply this out. So this is 1 plus 1 is 2, 3, and 0 and 0. Okay, that's not that bad. So the eigenvalues are 2 and 3, and eigenvectors are 1, 0, and 0, 1. Okay. So this means that sigma is going to be square root of 2, square root of 3. And if you're doing the full SVD, you would have an extra 0, or this would be a 2 by 3 matrix with zeros everywhere, like this. Or sorry, a 3 by 2 matrix. But I think for us, we're going to do like this partial SVD, like this, just SVD, as it's called in lecture. So we're just going to write it as a 2 by 2 matrix. If I'm going against the notation used in lecture, you should let me know, because I kind of want to be consistent. So feel free to correct me. Okay. And then V should be 1, 0, 0, 1, I believe. Okay, and now we want to find U. And so what we do is we basically solve this equation. Because if you multiply by V on the right of both sides, you have AV equals U sigma. That tells you what U should be. If you take AV and you divide by your the diagonal values of sigma, you should get U. And that's kind of what we're going to do. So I'll just kind of write that formula again, just so we remember it, what A is. We found that sigma, oops, were the eigenvalues, square root of them. V was 1, 0, 0, 1. Okay, and then looking at this is saying that AV should equal U sigma, because this here is orthogonal. And so that says you can just kind of solve for U. So you can say U1 equals A V1 over sigma 1, and U2 is A V2 over sigma 2. So where V1 and V2 are your singular vectors. So really, actually, I mean, if possible. So what'll happen is sometimes sigma 1 and sigma 2 could be 0. Right, in which case you can't divide by 0. And so U1 and U2 are not defined in that case, and you have to figure them out somehow else. But in this case, they're defined. And so we know what U1 is in U2. And so we can just do this. This is 1, 0, negative 1 divided by square root of 2. This is 1, 1, 1 divided by square root of 3. And I think maybe someone can correct me, but for the SVD you went over in lecture, you kind of just stopped here, right? So you found U1 was not like a full orthogonal matrix. You just found these two vectors. So you kind of, in lecture, correct me if I'm wrong, maybe you did something like U was just this non-square matrix. Sigma was here, and V was 1, 0, 0, 1. Great, so this is then your SVD. And if you multiply this all out, you get back A, in fact. So are there any questions on this? And also at the very end, so we should say, so these are the, these are normalized eigenvectors of A transpose A. So you should take the eigenvectors and then normalize them so that they have unit length. And so we did that already since they're already normalized of A transpose A. So these should be unit length. And then what this does, so after you find U1, you should technically divide by its norm as well, but actually it's already going to be unit length. This is already unit length, just because sigma 1 here equals the norm of AV1. That's kind of what it does. Conceptually, what's the difference between, so the question, conceptually, what's the difference between partial and full SVD? So full SVD, I'll do full SVD. The difference would be that U has this extra column in it. So we found U1 and U2, and now it has this extra column to make it orthogonal. Sigma since it's being multiplied by U, has to have an extra row. And V stays the same in this case. So that's like algebraically the difference. Yeah, besides the fact that the size of the matrix. So what conceptually is going on is that U1 and U2 are bases for a certain space. They should be bases, I guess, for the column space of A. So collectively, these two are bases for column space of A. And then what this is a basis for, I guess, the orthogonal complements of the column space of A. So you're kind of extending conceptually what you're doing, so remember when you diagonalize a matrix, what you're doing is you're finding a basis of eigenvectors, and the p's, when you diagonalize, let's compare this to diagonalization, are the columns are your basis of eigenvectors. So in diagonalizing, you have A equals P D P inverse, and these columns here are a basis of eigenvectors. And so that's kind of what U and V are. They're bases for certain spaces. And so in partial SVD, you're just finding a basis for the column space. But in full SVD, you're kind of extending that basis to a basis for the whole space by including a basis for its orthogonal complement. So conceptually, that's kind of what you're doing. Yeah. Remember saying that you can also diagonalize AA transpose to this process. Is there a difference between choosing A transpose A versus AA transpose? So the question is there a difference between doing this, I'm sorry, yeah, this or this? No, I don't think so. Basically, either one's going to give you singular vectors or singular values, the same singular values. I think you'll get this and this, but the vectors will give you columns of V versus columns of U. So it's kind of just doing the full SVD in a different order. Let's actually just do that. How about we just to compare? Because maybe I made that up. So let's figure it out. So A transpose is 1, 0, negative 1, 1, 1, 1. Also, the difference is one's a 3 by 3 matrix and one's a 2 by 2 matrix. So you're going to have to diagonalize the 3 by 3 matrix. Okay, so what do we get? 2, 1, 0, 1, 1, 1, 0, 1, 2. Okay, why don't we all spend some time diagonalizing this so we can get the eigenvalues? I'll just okay. Okay, great. So we find that the eigenvalues are 2, 3, and 0. So actually, I should have said the non-zero eigenvalues will be the same. You get 2 and 3, and so this tells you that your singular values are square root of 2 and square root of 3. And then your eigenvectors, I guess you can find. A minus 2 is 0, 1, 1, minus 1, 1, 0, 1. So the eigenvectors are one in the span of 1, 0, 1, which you'll notice this 1, 0, 1, we're finding u instead of v. Yeah, I'll put a different color. Right, instead of finding v first, we found u first. Right, so it's just kind of doing SVD in a different order. And then if we continue, you should find the other one, hopefully. A minus 3i equals negative 1, 1. Yeah, so, and then you should normalize these to get u, and then you should set v to be, I guess, a u, or, right, and then to find v, you can multiply by u transpose on the left. This implies so you can set v1 to be a transpose u1 over sigma 1, and v2 to be a transpose u2 over sigma 2. And so you're just kind of doing the SVD in a different order. Yeah, so are there any questions? I think in general, basically, you just want to choose whichever one, A transpose A versus A transpose. You just want to choose whichever one's easiest to diagonalize. That's how I choose it. Because it's easier to diagonalize a 2 by 2 matrix than a 3 by 3 matrix. Why don't you find the eigenvector for 0? Because, yeah, so there's the kind of the definition way beginning that I should have said these singular values, these are defined to be non-zero. At least I think. You only take I think the singular values of a matrix. Okay, so maybe this is going against the definition of the book, but I think the singular values in the matrix are always assumed to be the non-zero square roots of the eigenvalues. That might be false, actually. I don't know. But if you looked at, if you took eigenvalue for 0, then I guess you could just write. I guess you could just make U sigma be like a 3 by 3 matrix, and V would be a 3 by 3 matrix. No, actually, you don't want to do that. Yeah, I think you just do it for the non-zero eigenvalues, just by the algorithm. So maybe we can just do another practice example. Let's see. Does anyone have one they want to do? I don't actually have my book, so I fear that if I pick random numbers, they're going to be very hard to diagonalize. We can try the one I did last time. So find SVD. Okay. Right, so why don't we work on this for a little bit? This is basically all I have planned for today. I don't think there was much else that was covered in lecture. So I'm welcome to go over anything else that you want. But this is essentially my plan. Okay, so I can kind of work on this slowly, and you're welcome to ask me any questions, and then we can do whatever we want. So A transpose A. Nope, V. U. Okay, so are there any questions on SVD? Are there any questions in general for this area that we're doing? Otherwise, I think I might end section a little early, but I'll be on for anyone who wants to ask questions. And I will have office hours today at 3:30. the office hour schedule is on, is it not on B courses? If it's not on B courses, it's on probably Nikhil's website before we start using B courses that heavily. So on his website for the class, I think there's a text file with all of our office hours on it. So you can find it there. And then our Zoom links for all the GSIs are, those are on B courses. Is there a reason we know that A transpose A and A transpose have the same singular values and that they transposes of each other? Well, they're not transposes of each other. They're actually two different matrices. But why do they have the same eigenvalues? Let's see if we can try to prove that. Maybe we can look at A transpose A V equals lambda V and A transpose U equals mu U. I guess what if we multiply this by like A transpose on both sides? Then we get that A transpose U is an eigenvector for A transpose A with eigenvalue mu. And likewise, we get that AV is eigenvector with eigenvalue lambda. I suppose if this kind of maps eigenvectors of A transpose A to AA transpose, you kind of get a map. Kind of multiplication by A gives you a map between eigenvectors of A transpose. Which is multiplication by A. And I guess you know that these are both diagonalizable. Okay, so the proof is maybe a little more involved than I thought, but both of these are diagonalizable, so there's a basis of eigenvectors for both of these, like matrices. So you can describe this linear transformation on that basis. And yeah, I think just the fact that multiplication by A takes eigenvectors with eigenvalue lambda to eigenvectors with eigenvalue lambda. So the proof is it's a little more involved. I think it's not just like a one-line answer, but essentially it just comes down to this kind of reasoning. Yeah, it's not maybe so obvious. Yeah, they must have the same eigenvalues because multiplication by A takes all the eigenvectors here to eigenvectors here, but with the same eigenvalues of A transpose A. And so they must be just like some reordering of the eigenvectors and eigenvalues. Yeah, so can we use the fact that sigma transpose is just for the truncated SVD? So what exactly do you want to use or to show? I mean, yeah, I mean, I guess if you assume, right, if you assume A equals this U sigma V transpose, then you can just look at AA transpose and A transpose A. That's like the cleanest proof. If you just assume this, then where sigma is, diagonal, maybe not square, and U and V are orthogonal, then you can prove this pretty easily, right? Because then A transpose is U sigma V transpose, V sigma transpose U transpose, which simplifies because these are orthogonal. You get U sigma transpose U transpose. But then, yeah, because sigma is diagonal, essentially, then this middle part becomes an actual diagonal matrix with sigma 1, so, sigma 1 squared through sigma r squared, and then some zeros. Potentially. And then that's why you get some zeros when you diagonalize one of them versus diagonalizing the other. And then this becomes, this should be U transpose. Right, and so on one side you get that this is the diagonalization of A transpose A, and this is the diagonalization of A transpose, and you see that the diagonal values are the same. So that's maybe the easiest way to see that the eigenvalues are the same, if you assume you have SVD. Right. The only difference is one of them has different dimensions, and that's why you get some zeros when you diagonalize one versus the other. Right, so this one, right, so let's say sigma was, I don't know, m by n, then this is m by m, and this is n by n. So they're different dimensions. So for one of them, you might have something like 0, 0, and then it just ends right here. And for others, you might have these like zeros along the diagonal. That's what we found in the last example. We found that sigma transpose was square root of 2, square root of 3 in one of them, but sigma transpose sigma was, I think it was actually the other way around. Square root of 2, square root of 3, and then a 0. Why does V transpose V and U? Because they're orthogonal. That's because of this fact. So this becomes identity, and this becomes the identity. And now you have an orthogonal matrix times a diagonal matrix times an orthogonal matrix inverse. So that's the diagonalization. And here you have an orthogonal matrix times a diagonal matrix times the inverse of the orthogonal matrix. That's the diagonalization of A transpose. Can we first use truncated SVD on A, then transpose it? To get what? The SVD, that would be the SVD of A transpose, I guess. So keep in mind that these matrices are not transposes of each other. Right, yeah, it looks like it, but they're not. In fact, they're symmetric matrices. Right, if you transpose one, you get the same thing. So they're symmetric matrices, which is why you can actually do this orthogonal diagonalization, which is why it exists. Anyway, so maybe that answers why we don't look at this like third singular value here, just because we only care about the non-zero singular values. Okay, so I'm going to stop recording, and you're welcome to stay on and ask any questions.